Okay, so this is the last lesson in this unit, and we're going to be talking about the idea of phase diagrams. And when we talk about the idea of phase diagrams, I'm going to tell you that there's going to be a lot of stuff that I'm going to write on this graph, and I don't know, because there will be time, but I don't know if you want to write it as I go along or you want to pay attention real hard and then go back and rewrite it, just because there's so many things that I'm going to write on here that it might be easier for you to listen and then write later. I don't know. So with that in mind, this is a phase diagram, and this one specifically is for water. Now, all phase diagrams look pretty similar, but the values might be different, or the lines might have a little bit more of a curve to it or a little bit more of a slant to it. But the reality of it is everything about these is pretty much the same. So the first thing I want to address is what is going on this graph. And there's a lot of things, but one of those things is there's distinct areas in this graph. And one of the distinct areas is right over here, which is the solid area. So everything in this general vicinity, based on the conditions, would be considered a solid. Okay. And so basically, if I try to trace this, anything in that situation right there is going to be a solid. Now, this next part right here, man, I came up with this morning, and this is some high quality stuff right here. Okay. This next part right here is going to be a liquid. Oops. So basically, anything in this general area is a liquid, which then means that anything here could be considered a gas. So anything in this general area could be a gas. Now, each, the line, for example, the line CB, and I'm going to kind of try to write this as a statement of fact. So the lines, line BC or line BD, okay, or even to a certain extent line AB, are when the substance is at equilibrium between those two states of matter. And what I mean by that is that from line BC, anywhere along that line, when the conditions are what they are, the pressure is something and the temperature is something, that substance can be a solid and a liquid quite kind of at the same time. And what I mean by that is if you take a chunk of ice and you put it on the table and you watch it melt, there's a point in time where you have water and solid at the same time in the same cup. Does that make sense? That's what we're talking about at equilibrium, that where they're basically at the same time, at the same temperature, and at the same pressure. There you have the opportunity for water to be solid and liquid at the same time. So with that in mind, going across that line is a melt. And going across this line in this direction is a freeze. BD, for example, going across this line is a boil. Going across from like left to right, I suppose, and going from right to left, we would say is a freeze. Okay. Not a freeze. Shoot, not a freeze, not a freeze, not a freeze. A condense. Sorry, I misspoke. Now, okay, so I've gotten a lot of things going on here, and I'll come back to a couple of other things, but now I need to talk about some very specific information. All right, one of those specific pieces of information is this number right here. Does anybody remember from the gas law unit, which feels like forever ago, what a pressure of 1 atm meant? 1 atmosphere. Yes. That's even further back in time, atomic mass unit. But in this case, we are talking about we talked about 1 atmosphere as it related to standard temperature and pressure. We said that at 1 atmosphere, so standard temperature and pressure was 1 atmosphere of pressure and 0 degrees Celsius. And on this data table or graph, this is our normal atmospheric pressure. So it's our normal atmospheric pressure. Now, the reason why that's important is because at 1 atmosphere, if I go straight across to here and go straight down to here, that intersection is what we call the normal melting point. So at 1 atm, go straight down. At 0, that's the normal melting point of water. If I continue this line straight across, when I get to this intersection here and drop it straight down, this is known as the normal boiling point. Okay. So I can identify the normal melting point and the normal boiling point based on where the line for the line of equilibrium between solid and liquid and between liquid and gas is in relation to 1 atmosphere of pressure. Now, there's another really kind of important set of numbers on here, and that this other one is this number right here. This is called the critical point. Critical pressure. And if I take this critical pressure and go all the way across to here, and then I take that part and go all the way down to here, not my best artwork, right? That gets us to something that we call the critical point. This is the point where it's the last temperature and pressure that a liquid can exist. And so down here, we would call this the critical temperature. So we have a critical pressure, we have a critical temperature, we have a critical point. And essentially, it's kind of where this line ends. Now, there are a couple of other points that I want to make, that I want to spend some time talking about, and one of those is this spot right here. When I circle that spot right there, what is true? What could you predict might be true about the state of matter or matters of that substance? Like, don't overthink it. It's not a trick question. The answer was it's super hot. The answer to that question is not necessarily. It might be, depending on the substance. But I purposefully made that circle pretty big to indicate that it's kind of coming to a point at three different states of matter. We call that the triple point. Okay. Now the triple point is when solid, liquid, and gas exist at equilibrium or at the same time. Now, an example of this would be sometimes in the winter when we have snow on the ground, right? We have snow on the ground, and sometimes it gets foggy when there's snow on the ground. Okay. Snow is an example of solid water, right? It's ice. Fog is sort of an example of like gaseous water, right? Because it's kind of floating around in the air. And then if you happen to be out in a situation like that, more often than not, the ground is going to be wet. And if the ground is going to be wet, that means that there's liquid water present as well. So at that instance, that particular night when it's foggy and there's snow and all of the things are happening at the same time, the conditions are essentially right for the triple point of water to exist. You have gaseous form of water, solid form of water, and liquid form of water all outside at the same time. It's just a treasure. Now, those two more things we need to talk about before we're done for today. One of those things that we need to talk about is what happens when you go from a solid directly to a gas, and that's called sublimation. If I can spell. And that does happen. And then there's an instance where you go from a liquid or from a solid or a gas directly to a solid, and we call that deposition. Now, the best example I can possibly give you of sublimation is there these solid air fresheners that you get like at the dollar store that's like looks like a little triangle. Actually, it looks like an upside down Solo cup, and you like twist it up, and when you twist it up, like there's this forbidden jelly on the inside. You know what I'm talking about? It like looks like that would be delicious to put on a piece of bread or toast, but you know you shouldn't eat it. And then you twist that thing up and you put it like on top of the toilet tank or something like that. And then you're like, oh, that forbidden jelly is going to be great later. And then you come back like 30 days later and the forbidden jelly's gone. Magic. Where did it go? It's not magic. It actually went from that solid form directly into the gaseous form of that substance as smell or stink. Okay. So that's how some air fresheners work. Another less forbidden jelly example would be during the winter time. Sometimes we have like 6 inches of snow on the ground. And when you have like 6 inches of snow on the ground and it's like wicked cold, like negative 10 degrees Celsius for like a long time, like say a whole week, and you're standing in the house and you're looking outside and you've got the 6 inches of snow, and all of a sudden over the course of a few days, that 6 inches of snow gets shorter and shorter and shorter. And maybe it's like 2 inches of snow. What happened there? Well, I'll tell you what happened there. It didn't melt because it was too cold for it to melt. It actually sublimated. It went directly from solid snow to solid water to gaseous water by sublimation. So that's another example of that there. All right. There's so many things that I've written on this. It can be overwhelming. I get it, but let's try to answer a couple of the questions that are on the bottom of your page there. Yes.
above the critical point, what happens to, does the water turn into something else, or?
So the question is, what happens above the critical point? The answer to that question is at that point, any liquid could no longer be liquid, so it had been converted to gas at that point. So essentially, basically, above the critical point, to the right and even to the left-ish is going to be this gaseous area. But the truth of the matter is that in very rare instances are we actually living at the critical point, because, for example, the pressure for the critical pressure is like 218 atm, which is like we would not exist if we were at that pressure. Okay. And the critical temperature is like 374 degrees Celsius, right? So like at that point, like we barely can handle it when it's 100 degrees Fahrenheit, which is like not 100 degrees Celsius. So the point that I'm trying to make is that somewhere around there, you probably would all have become a gas, but even past there, we could get closer to what we call plasma, but that's a whole nother dump of energy, and we're not going to go into that in the scope of this class. So, but back in the scope of the class, phase diagram questions: what letter or letters describe the line that defines equilibrium between solid and gas? I would write for that, from solid to gas would be the line AB. Okay, that's where you would talk about sublimation. Which letter best describes the equilibrium between solid and liquid? I would say the best description of that would be BC. And then which letter best describes the relationship between, or the equilibrium that was supposed to be between liquid and gas? And so in this instance, it would be something like BD. Okay. Now, if you put them if you don't put them in alphabetical order, like if you put BA, CB, or BD, or DB, I actually don't care. That's fine with me, just as long as you're correctly identifying the right thing. Questions? Okie dokie. I'm going to leave this up here in case you may want to copy it. However, your homework tonight is to do the next worksheet in the packet, which is a two-sider. And you have some time to work on that right now, so I highly suggest that you do so.